Okay, the numerical is a simply supported overhanging beam is loaded with point load as shown in figure. A cast iron beam of C section with top flange 150 mm by 15 mm, that is this portion, 150 by 15. Bottom flange of 200 mm by 20 mm, that is this one, and a web of 15 mm by 200 mm, that is this vertical portion is called as web. The allowable stress in tension and compression are 120 megapascal and 90 megapascal. Find the safe value of load W on the overhang. That is this load W we will have to calculate. Now quickly let us start. Now in this first thing is we need to find the maximum bending moment from this diagram. In this diagram, I have to locate the center of gravity as well as the moment of inertia, right? I think this numerical is for 10 or 12 marks. This is from my old pattern. In your exams, you may not get this complex numerical. If at all they give an unequal or asymmetric cross section, they will either give the IXX IYY value along with location of center of gravity, or some value will be given by which it will be little simpler. It may not go this lengthy as we are going to do now. Okay, first let us find the center of gravity for this particular cross section. Now, since this is asymmetric in both x-axis and y-axis, I am taking this point as my reference. So, this O that you see here is my reference. It's not visible. Let me make it black. Yeah, this is better. This is the origin with respect to which I am going to find x bar and y bar. So he has given a neutral axis here. I will draw another, or mm yeah, for I will need x bar. Well, that is not required, right? I will need to find only this y bar, right? X bar is not required, right? So for finding y bar, we have this expression. First, I'll write location of neutral axis Na, right? That is basically this axis. So with respect to the bottommost fiber, I'm doing now. So how do we do this? Y is equal to, we did yesterday, summation of individual area into the distance between its from the reference to its own center of gravity, right, divided by total area. So it is a1 into y1 plus a2 y2 plus a3 into y3. I'll put them in a bracket by a1 plus a2 plus a3, right? Now I will need all these areas and everything later also for moment of inertia. So what I will do is I will calculate a1, a2, a3 first, right? So a1 is equal to, this is 1 for me, so it is 200 into 20, that will be into 4,000 mm square. Then A2 is equal to 15 by 200. 15 by 200. So that is 15 into 2 is 30. 3000 mm square. And A3 is equal to 150 into 15. Let me do this. 2250 mm square. Now I have all the areas. So I can calculate some more. Okay. Y is equal to 4000 into y1. Now this is my reference. So from here at a distance of 20 by 2, that is 10 mm, is the center of gravity for this. So 10 plus 3000 into CG of A2. So this is 2. So this will be 200 by 2, that is 100 mm from this top surface, plus 20. So it is 120 plus 2250 into 200 plus 20, 220, 220 plus 15 by 2, that is 7.5. So 227.5. That is the location of CG from bottommost fiber, divided by 4000 plus 3000 plus 2250. This will be mm. Y is equal to, let me calculate this, 4000 into 10 is 40,000 plus 3000 into 120 plus 2250 into 227.5. It is this much, divided by 4000 plus 3000 plus 2250. It is 98.58, 98.6 mm, right? So from the bottommost fiber at 98.6 mm, I have the neutral axis, right? You need not calculate x bar for this because CG will be on this, and for finding the moment of inertia, I will use the parallel axis theorem. So for that, y bar is sufficient for me. I don't need x bar also. Okay. So let us now find moment of inertia. So for finding moment of inertia, I will have to first calculate I1, I2 and I3. So I1 is equal to B D cube, right? So B is 200 and D is 20. So 200 into 20 cube by 12. So this is 200 into 20 cube by 12. Just and paste it here. One decimal is sufficient for me. Mm raised to 4. Okay. Similarly, I2 is equal to B here is 15 and depth is 200 into 200 cube by 12. So 15 into 200 cube by 12. Just copy and paste that value. ml raised to 4. Then I have I3. I3 is what? B is 150 and depth is 15. So 150 into 15 cube by 12. 150 into 15, sorry, cube by 12. So this ml raised to 4. Now I have to calculate H1, H2 and H3. H1 is equal to, now H1 is, this is G1, G1 to neutral axis. The distance between G1 to neutral axis we have to find. That will be Y minus 10. So it is 98.6 minus 10 and that is 88.6 mm. Similarly, H2, the location of G for this is 2, it is 100 mm above this surface, correct? So 100 plus 20, 120 mm from the bottom is the CG, minus, I have to do this Y, 98.6. So that will be 120 minus 98.6, sorry, 21.4 mm. Then H3, uh, from the bottom surface, the location of CG is 227.5. We have calculated this earlier. 20 plus 200, 220 plus 7.5. You subtract 98.6 from that. 227.5 minus 98.6. So that will be 128.9 mm. Okay, now I have I, H1, I1, I2, I3, H1, H2, H3, and also I have A1, A2, A3. Now I can calculate the moment of inertia about the neutral axis, about this axis of the entire cross section. So I is equal to parallel axis theorem. Parallel axis theorem says INA is equal to I1 plus A1 H1 square plus I2 plus A2 H2 square plus I3 into A3 H3 square. Now let us write that I1 plus A1 into H1 square plus I2 plus A2 into H2 square plus I3 plus A3 into H3 square, right? So this will give me the total moment of inertia of this cross section about the neutral axis. So this is I is equal to, now I have to substitute the values. I1 is this much plus A1 is 4000 into H1 is 88.6 square. Okay, that is the first term. Second term is I2 is this plus A2 is 3000 into H2 is 21.4 square. That is the second term. Plus third term is I3 is this. Okay, I3 plus uh, A3. A3 is this into H3 is 128.9 square. It's a huge equation. Now let us try to calculate this. So I1 is this much plus 4000 into 88.6 square plus this plus 3000 into 21.4 square plus 42187.5 plus I think area I substituted wrong here. Nobody pointed out also. This is 2250. Glad that I saw. Plus 2250 into 128.9 square. So this is the total moment of inertia of the given cross section Nm raised to 4. Okay, so this is the moment of inertia for the given cross section. I will just put it here. Okay, now I have calculated the moment of inertia. Now next part is to find the maximum bending moment of this particular beam, right? So it is a simply supported beam. It's a overhanging beam which is simply supported at A and B, and B and C is overhang. The length between A and B is 900. Between B and C it is 200 mm. Right? Now first I have to find the support reaction. So for finding support reactions, first let us take moment about point A, taking moments about point A, we get this load W into perpendicular distances 900 plus 700, so that will be 1600 mm. This is downward, right? So that will come later. Before that, I have RB into 900, and this will be minus W into 1600, and that is equal to 0, right? Or RB is equal to 1600 by 900 is, oops, writing a fraction here, just a minute. 1600 by 900. Oh, okay, it's a proper fraction. So 16 W by 9. I'll keep it like this only. Uh, and the unit is in Newton, right? I'm taking this in Newton. Now, sum of all the forces is equal to 0. So, Ra plus Rb is equal to W. There is only one vertically downward force, W, or Ra is equal to uh, W minus 16 W by 9. So 1 minus of this will be minus 7 by 9. This minus 7 W by 9 Newton, right? So I'm going to write this, draw this beam now. So this is the beam. This is point B. So at point B, I have a reaction like this, and at point C, there is a load, and point A, the reaction is negative. That means the direction is downwards, right? Negative force of the reaction indicate it is downward direction. Now let me just name this quickly. A, this is B, and this is C. RB is equal to 16 W by 9. This is W, and this is 7 W by 9. So we have to find the bending moment now. See, the bending moment will be 0 at A and C. It is the this is the end support and this is the free end. So bending moment will be 0 at these 2 points. So the maximum bending moment will be at point B, which is the support. So Bm at B is equal to, you can either take left side or right side, you will get same from both the sides, and this will be negative bending moment, right? So the beam will be hogging, it is not sagging, it is hogging bending moment. Okay, so yeah, let me take left side, that is simple. So that will be W is the load into perpendicular distances, this, that is 700. Okay, so this will be 700 W Newton mm. That is the maximum bending moment at point B. Now we have to find the value of this W. Now let us use the bending equation. So from bending equation we have what is that? Bending stress is equal to my by I, right? My by I, you remember like this, my and I, right? My divided by I, that will give me the bending stress. Now here the fibers above the neutral axis, this is my neutral axis, N A, neutral axis. All the fibers above the neutral axis is subjected to compression. The fibers below the neutral axis is subjected to tension. Now he has given allowable stress in tension and compression both, right? So allowable stress in tension is 120 megapascal and in compression is 90 megapascal. This is a cast iron. So cast iron is I don't know, the value must have been swapped. Anyways, whatever he has given we have to use, because cast iron is not good in tension but it is good in compression. The value should have been reversed, but this is an exam problem, we had to solve it with these values only. So let us try to find this. Now see, the beam is bending like this. I will show it in red color, right? Because of loading, the beam is going to bend like this, right? Rather, it is like this, right? So the beam, after applying the load, it is going to bend in this way. So it is reverse now, right? The fibers on the upper side of the neutral axis will be undergoing tension and the fibers on the lower side will be under compression, because we have seen the numerical in last class where the loading was like this, right? So load was applied at the center, or there was a UDL, and the beam was bending like this, right? It was bending in this way, but now here it is reverse. So the upper fibers are subjected to tension and lower fibers are subjected to compression. Now I have to find W based on compressive stress, permissible compressive stress and permissible tensile stress. So considering tension, right? Considering tension in the beam, uh, above the neutral axis, right? So in this case, the tension is in the above, the fibers above the neutral axis. So I am substituting the values now. The permissible tensile stress is 120 megapascal. So 120 is equal to bending moment. Maximum bending moment is 700 W. 700 W. This is in Newton mm. Okay. Into Y value. See, Y is from the neutral axis to the topmost fiber. So you have to just find the total height of the section and subtract Y from that. So total height of the section is 20 plus 200, 220 plus 15, 235. 235 minus Y bar is 98.6. So that is 136.4. 136.4. Yeah. So that is my uh, my by by I value. I is this much. And better copy this and I will put it there. Right? So from this I will get the value of W. So let us solve this 120 into 8033346 3.3 is this by 136.4 by 700. So or W is equal to Newton. So this is about 100.96 or I would say 101 kilo Newton approximately. Okay, that is the maximum load you can apply on this beam for the beam not to fail in tension. There is one more criteria, that is compressive failure. So using that, I will calculate again, considering compression in the beam, that is in fibers below the neutral axis. Okay. Now I have to find this length of neutral axis from the bottommost fiber, that I have already done, which is 98.6 and permissible compressive stress is 90 megapascal. Using this, let me find W. So 90 is equal to 700 W into 98.6 by I is same 80333463.3. Okay, I'll just copy this so that I don't have to type again. So 90 into this by 98.6 by 700. So this is very less. W is equal to Newton. How much is this? 104 kilonewton, correct? Or 104.75 kilonewton. Now, which one should we select? We discussed this yesterday. Always we have to select that which is having lower value. The permissible value should be always the one which is lower. So in this case, in tension, when you consider the load due to tension is 101 and load due to compression is 104. So if you apply 104 kilonewton, then the beam will fail due to tension. So if you apply 101 kilonewton, then beam is safe both in tension and in compression. So just write a statement like this: maximum permissible load on the beam is 101 kilo tensile. right? Based on tensile, whatever you have got, that is the maximum load which is permissible. Is there any questions? Are there any questions?